Okay, so now we want to see that how are we going to correlate the surface area with respect to the stress which had been acting in a zone. That is, suppose if there is a force that is sigma 1 acting in this direction and sigma 2 acting in that direction, then if the surface is as and the angle is alpha with respect to the coordinate axis, so obviously the force that is acting along this direction will be s into this area, and acting along that direction will be s into this area, because s has an angle of alpha if this is with this direction and it is alpha, so s into sine of alpha into sigma 2 will be the perpendicular vector, and the s into cos alpha into sigma 1 will be the horizontal vector in terms of the axis when the object is working like that. And if we now separate the overburden induced vertical stress sigma 2 from the total stress state, we are left with a plane state of stress. Okay. Now, when the shape is small enough and the weight is negligible as compared to the surface forces that act upon it, the forces acting upon such surfaces or rock mass are products of stresses and the area that is acting it is acting upon, that is s cos alpha is sin alpha into sigma 1 into sigma 2 f1 into f2, and if sigma 1 and sigma 2 are the forces along the axis which are perpendicular to each other, and we are trying to divide the area into smaller parts or smaller partitions, as we have tried to do this in this case also. Now obviously this thing is going to be that normal force which will act along this surface, that is only along this direction, that is the normal force, that is normal stress that is acting along this direction, that is vector n, will be what? We will have to again divide this into two parts, and if it is alpha, then it will be what? It will be this arm versus this arm, which is the meaning that is sine alpha. Okay, and this is sigma 2. This is what? Sigma, whatever it is, sigma 2 into cos into alpha, or there is sigma 1 into cos into alpha, and if it is being multiplied by the sine alpha or the cos alpha term, then what we will find in this case of normal stress over this plane, will be sigma 1 into s into cos square alpha, and for this component, the component which will be added like sigma 2 into s into sine square alpha. Okay, and which we can say that's Fn, that is the force that is acting normally to this surface. Now we can do it from mathematically, that is Fn by s will be sigma 1 into cos square alpha plus sigma 2 into sine square alpha. Now cos square alpha, it is what is cos square alpha? Now cos 2 alpha plus 1 by 2, and this is cos 2 alpha minus 1 by 2, or plus 1 minus cos 2 alpha by 2. That is mathematical, Fn by s. Now what we will find here is that if we take some side changes, sigma 1 plus sigma 2 by 2 plus sigma 1 minus of sigma 2 by 2 into cos 2 alpha will be Fn by S, and this is a very generalized terminology of any force or the normal force acting upon a perpendicular surface, where we know the sigma 1 and sigma 2 as well as the alpha, which is the angle of the slip or the angle of stress or the angle of strength through which the surface had been fractured or ruptured. And the shearing components along the AB, remember the sense of the shear from the stress sigma 2 is opposite sign that of the sigma 1. Okay. Now this is how this can be expressed mathematically in a plane. Now the question is that whenever a rock is undergoing metamorphism, there are certain minerals in the rock like this and smaller minerals like this, and every single mineral constituent in the rock has their own identity. Suppose this is plagioclase feldspar, this is pyroxene, this is quartz, and we are acting or we are introducing some of the stress into it, and the minerals will act accordingly to their orientation as well as the applied stress, because different minerals act different because of their different types of elastic properties or plastic properties. Quartz that becomes plastic in 600 to 700 degrees Celsius, whereas pyroxene, this can only become plastic in a temperature of about 800 degrees Celsius. Plagioclase feldspar, which gives you an intermediate 750 degrees Celsius, and it also depends upon composition, whether it is rich in calcium and sodium. And that is the implication of geology in a normal physical behavior, that how the minerals or the phases can change the physical attributes in a rock while a stress is being applied to the rock. And that is the implication of geology onto physics, that is the applicability of it to the subject. And whenever we are going to trying to find in the microscope, we will see different types of behaviors, and that's why we will see that some of the grains might show subgrain rotation process. That is a signature of dynamic recrystallization at a high deformation rate or high temperature, whereas the other minerals might just show some evidences of bulging recrystallization like garnet. So different grains that those are acting differently in similar situations of stress, and that's how we can identify from their solid state deformation properties that what might have been the grade of the rock, or what might have been the mineralization or the metamorphism that the rock had gone through. However, the basic will remain the same, that is a plane or a surface that is being acted by stress. It is two-dimensionally we are observing this. We can also observe it in three-dimensionally, where the tensors can be introduced and we can solve it mathematically. Okay.